So today's lesson is on binomial expansion and Pascal's triangle. So what does this mean? Expanding x plus 2 quantity squared doesn't mean this. Ha ha ha. Right? Just physically expand it, right? What it means is to actually multiply this out, like take it and put it into standard form. So this would mean multiply x plus 2, right, times itself twice, times x plus 2. And if you do FOIL that out, you'd get something like x squared plus 4x plus 4. Okay, so that's fine. That wouldn't take too much time. However, if I asked you to do something like x plus 3 to the 4th power and expand that out, this would take quite a bit of time, as we'd have to do x plus 3 times itself 4 times. So we'd have to multiply two of these together, get our answer, multiply that by an x plus 3, etc. And obviously that takes quite a bit of time. So what we're learning today is how something called Pascal's triangle and binomial expansion fit together, and how Pascal's triangle will help us do this task a lot faster. Okay, so what is Pascal's triangle? So it's a triangle that we can create by starting by making a little triangle with 3 ones. 1, 1, 1. Okay, and our rule here is we're going to continue with ones on the outside of our triangle. And anytime there's a space in between two numbers, like above, right, there's some space in between these two ones, we're going to add these two digits and put the answer in that next line. So 1 plus 1 gives us 2. So to create our next row, we put some more ones on the outside. There's some space here between 1 and 2 above, and the digit we put here is their sum. 1 plus 2 is 3. Okay, similarly, there's a space here between 2 and 1, and we'd write their sum. 2 plus 1 is 3 below that. And to continually create rows, we just keep following this rule. So in this space, we'd add the 3 and 1 above it to make 4. These two 3's add up to 6. 3 and 1 adds up to 4. Okay, and then we could continue this pattern. This would be 5, 10, 10, 5, and 1. Again, just adding those numbers above. And this really could keep going, of course, and there'd be lots and lots more rows that we could fill in. Okay, so instead of my terrible drawing, here's some nice printed numbers, giving us the first few rows of Pascal's triangle, following again that same pattern. So let's take a look at binomial expansion, and we're going to look at kind of generically taking something like a plus b to the 2nd power and doing a times a plus b times a plus b and getting our answer, etc. So that's what this next chart represents. So if you actually started with a plus b to the 0 power, well, if you remember about properties of exponents, anything to the 0 power is equal to 1. So that whole answer just becomes 1. If you did a plus b to the 1st power, well, that's just a plus b. And so you can see that written here, a plus b. And I know that I have written the kind of normally hidden coefficients of 1 and 1, and normally our hidden exponents of to the 1st power and 1st power. Okay, for a plus b squared. Okay, so you haven't seen that expansion. We'll do this first one. A times a makes a squared. A times b makes ab. Okay, we've distributed the a through. B times a is another ab. Again, we try to keep those alphabetical so we can see our like terms. And b times b makes b squared. So if we were to combine them, I would get a squared plus 2ab's plus b squared. And you can see that answer in this next line, a squared plus 2ab's plus b squared. Again, I've written some coefficients of 1 in front of these, and things that are to the 1st power, we place those exponents in, just so we can see some patterns here in a second. Okay, so if you took a plus b squared times another a plus b, we end up getting this line as our answers. A plus b to the 4th gives me this line as the answer, and etc. So right now, we want to stop and try to locate. As you can see, I've tried to design this purposefully over here, some things that go together between Pascal's triangle and our binomial expansion. And hopefully you see it already, that if we looked at our coefficients, 1, 1, 1 and 1 again, 1 and 1 again. 1, 2, 1, 1, 2, 1, etc. Right? 1, 3, 3, 1 here, 1, 3, 3, 1 here, etc. So I'm going to stop scribbling all over this because hopefully you see the pattern now. 1, 4, 6, 4, 1, 1, 4, 6, 4, 1, etc. Okay, that's great. So now we see that the numbers from Pascal's triangles represent the coefficients, or the numbers in front of these variables. What other patterns can we see here? If I skip specifically, let's just skip down to this squared line. Notice when it's this quantity squared, if I look at just the variable a for a moment here, we've got a to the second, a to the first, and you could even think of this last term as a to the 0 if you want, but no more a's. Now if we look at our second variable in here, b, you can see from starting from the right, I have b to the second, b to the first, and if I continue this way, you could say even b to the 0, or essentially no values of b. So there are some nice patterns here. Let's check out when we are in this expansion to the third power. It starts a to the third. Our next term has a to the second. Our next one has a to the first. And our last term would have a to the 0, or no a's. If we look at our second variable of b, this kind of fills in from the right. Again, from the third level, this is b to the third, right? Or an expansion to the third. Then b to the second, b to the first. You could even think of our first term as not having any b's. Okay, so you can see there's some nice patterns here. When we're in the fourth power, our b's fill in backwards from left to right. B to the fourth, b to the third, b to the second, b to the first, and no more b's. And a's fill in from the left. A to the fourth, a to the third, a to the second. And so if we use these patterns, if we know I'm starting with an expansion of 4, that my powers of a would start to the 4, starting from the left and descending. And my powers of b would start from b to the fourth and descend as we go to the left. Then we can fill in all of this generic expansion. Okay, and we'll be able to use this generic expansion to answer terms when it's not just a and b, it's things like x and 3, by substituting in for a and b. So one thing we usually want to notate here, though, is that Pascal's triangle at this top level is really not, we wouldn't call this level 1, because it's an expansion to the 0 power. So we actually refer to this as the 0th level, or level 0 of Pascal's triangle, and the next layer down would be the first level, etc. So level 1, level 2, etc. So this is the first 2, 3, 4, all the way down to the level 4 of Pascal's triangle. All right, as you can see here, this is kind of the honeycomb version of Pascal's triangle, marked with some of our levels, all the way down with our pattern to level 7, which is probably about the furthest we'll need it for most problems. Okay, so let's try that second one that we were given in the beginning. Expand x plus 3 to the 4th power. And the first thing we're going to do is find the generic expansion of a plus b to the 4th with Pascal's triangle. So because this is to the 4th power, we need to go to the 4th level. So remember, this is level 0, then 1, 2, 3, 4. So obviously I've already marked them on here for us, but we are in the 4th level. So the first thing we're going to do is write down those coefficients. 1, putting some space between these, 4, 6, 4, and 1. Okay, now remember there were some nice patterns that went in with our a's and b's. If we're starting from the 4th power, it starts on the left with a to the 4th. Our next term would have a to the 3rd, a to the 2nd, a to the 1st, and our last term you could say has a to the 0 or no a's. We can fill in backwards our values of b. Remember, it starts from the right, b to the 4th. Again, that's from our expansion here. B to the 3rd, this term has b squared, b to the 1st, and our first term has b to the 0 or no values of b. Now all we need to put in between these is some plus signs. And this is the generic expansion with a and b in it. Okay, so we don't want directly a and b. Instead, where we see a, we're going to substitute in x. When we see b, we're going to substitute in positive 3. So notice that both of those are positive values. So let's go in and do some substitution. Okay, so here I filled in every a to our exponent with x to that exponent. Next I'm going to fill in our values of b. Okay, and there's all of our values of b replaced with 3. Remember, since we're substituting in, we're using parentheses. And now that we're simplifying this, we need to follow order of operations. So we need to go through and evaluate all of these exponents first. All right, so now we've evaluated all of our exponents. Notice again, things like x cubed are now inside the parentheses. So I just want to represent these 3 quantities still need to be multiplied, etc. So now we'll go ahead and multiply things through here. We get 1x to the 4th. We're going to end up with positive 12x cubes. Of course, our 1x to the 4th, we can just leave as x to the 4th. Okay, plus 12x cubed. 6 times 9 is 54x squared. 4 times x times 27. 80 and 28 is 108x. And 1 times 81 is 81. So this would be if I took x plus 3 times x plus 3 times x plus, did that 4 times and wrote that whole thing out, we get our final answer here. And yeah, it was still a decent amount of work. Obviously we went a little slower on this problem probably than we could on some additional problems, but this is still a bit faster. And imagine if I gave you this problem to the 7th power, well, by far, binomial expansion with Pascal's triangle would have been much quicker. Okay, let's try another one here. We're going to do 2x plus 1 to the 5th power. Let's start with the generic expansion of a plus b to the 5th. And so we're going to use Pascal's triangle. This time we're going to go to level 5 now with coefficients 1, 5, 10, 10, 5, and 1. Remember, since this is an expansion to the 5th power, we're going to start with our variables to the 5th power. A to the 5th, a to the 4th, a to the 3rd, a to the 2nd, a to the 1st. And our last term having no a's, filling our b's in backwards, b to the 5th, b to the 4th, etc. Okay, then we can just put in our addition signs between them. So all these terms are added together. And there's our generic expansion with a plus b to the 5th. One other thing to notice that I didn't point out earlier, in an expansion to the 5th, each term, our 2 variables' exponents, will always add up to 5, right? Including the first and last term, of course. So extra pattern there that we'll utilize a little bit later. Okay, so let's substitute in here, where a is 2x and b is positive 1. Now, if this was minus, then yes, we would plug in b as negative 1 in our parentheses. So be very careful. Okay, here I've replaced every a with the quantity 2x and raised it to the appropriate power. And every value of b has been replaced with positive 1 and again raised to the appropriate power. So now we need to evaluate our exponents here. Okay, so keep in mind 2x to the 5th means 2x times, right? 5 of these. So in fact, both parts end up becoming to the 5th power. So 2 to the 5th power is 32, and x to the 5th power, 32x to the 5th. For our second one here, 2x to the 4th, 2 to the 4th power is 16, and then x to the 4th. I'm just doing the ones in blue here are powers of a, so 2x cubed, this becomes 8x cubed, 4x squared, 2x to the 1st, which is just 2x, and that's it for our powers of a. Filling in b is going to be relatively simple. 1 to the 1st power is just 1, 1 to the 2nd power is 1, 1 to the 3rd power, right? This is going to be pretty easy, 1 and 1. So lastly, to simplify these, to get our final answer here, 1 times 32x to the 5th, 32x to the 5th, 5 times 16 times 1 is 80x to the 4th. 10 times 8 times 1 is also 80, this time x to the 3rd. 10 times 4 times 1 is 40, x squared. 5 times 2 times 1 makes 10x, and 1 times 1 is 1. And there's our expansion of this thing to the 5th power. Okay, here's another problem. This time we're only going to do it to the third level, an expansion of this to the third. But let's do an example with a negative second value and if we have a different variable. Okay, so let's start with our generic expansion of a plus b to the third power. So we look again at level 3. Remember, the top level is level 0, and our coefficients are 1, 3, 3, 1. Fill in again if our expansion is 3. Start with to the third power for each of our variables, a to the third, a squared, a to the first, and fill in b backwards, b to the third, b to the second, b to the first, where the last one has no more b's. Again, I talked about that pattern before, that these should also, the two exponents, add up to our expansion. Okay, here a is going to be represented by 2x and b is represented by negative 3y. So we do need to keep that sign with it because it was plus b in the generic expansion. Okay, so now I've gone ahead and filled in everywhere with a with 2x and everywhere with b with negative 3y. Let's evaluate our exponents next. 2x cubed becomes 8x cubed. 2x squared is 4x squared. The quantity of 2x to the first is just 2x. And now let's go back and do our powers of b. Negative 3y to the first is just negative 3y. Negative 3y to the second is positive 9y squared, right? Negative 3 times itself twice. And be careful here as well. Negative 3 times itself 3 times is negative 27y cubed. So lastly, let's go ahead and combine all of these. We get 8x cubed, right, times our 1. 3 times 4 times negative 3 is negative 36. We're going to write this as minus 36x squared y. Okay, and we tend to keep these variables alphabetical sometimes, but we're going to say just keep them in the order that they're given here for a and b, or we'll write a to the left and the value of b to the right. Okay, for our next term, 3 times 2 is 6, times 9 is 54, positive, so plus 54, x to the first, y squared. And 1 times negative 27 is negative 27y cubed. And this is our answer. That thing times itself 3 times. Okay, let's look at a couple of different questions here. What if it wants me to find, instead of the full expansion, just a specific term? Find the fourth term in the expansion of 3x minus 2 to the fifth power. So pretty big expansion there. So one, I already know I'm way down here at level 5. Remember again, the top level is 0. So there's a lot of terms in, right? If I write down my coefficients, 1, 5, 10, 10, 5, 1. Now note that I don't need the full expansion. It just wants the fourth term. So that actually means from the left. So this would be the first, second, third, fourth term. So the second 10 here would be the coefficient of the generic expansion, right? A plus b to the fifth. And since I only want this term, we can fill in just this term. So you could remember, of course, that this is a to the fifth, a to the fourth, etc. And that this will be a to the second. And then backfill your b values, or, as mentioned earlier, remember that once I get one of these two variables, if this is to the fifth power, they need to together add up to 5. So once you get a squared, you might deduce that it has to be b to the third there. Right? All these ones I'm filling in right now are completely unnecessary because we're only interested in this term, the fourth term in. So it's going to save us a lot of time. So for a, we're going to substitute in 3x, and for b, negative 2. And all I need to calculate is plugging in 3x squared and negative 2 to the third. Okay, evaluate our exponents. So 3x times itself twice is 9x squared. And negative 2 times itself 3 times, this comes back out negative 8. So lastly, we're just going to multiply all of this together. 9 times negative 8 is negative 72, times 10 is negative 720, and our only variable is x squared. This would be the fourth term in that whole expansion without me needing to find the whole expansion, right? We just needed to find the fourth term in, again, 1, 2, 3, 4, and then fill in our variables in our generic expansion and calculate just that one term. One last one here. Find the seventh term in the expansion of -5 plus 2y to the seventh. Okay, so even though it's put the constant first here, we're going to keep that in the same pattern of a and b when we do eventually go plug in, and this would be positive 2y. So again, we want the generic expansion of a plus b to the seventh, but since we only want the seventh term, we don't even necessarily have to write out all of these terms like we did before. So let's go to level 7, right, since this is to the seventh power, and let's count in to our seventh term. 1, 2, 3, 4, 5, 6, 7. So in fact, the seventh term happens to have a 7 in it. Okay, so our coefficient there would be positive 7. So we're just finding this one single term, focusing in there. And if you remember, this would be a to the 7th, 6th, 5th, 4th, 3rd, 2nd, a to the 1st. And if we filled in our b values backwards, b to the 7th, b to the 6th. Or again, once I found one of these, which probably would have been faster to find b, remember that they both need to add up to 7, since we're doing an expansion to the 7th power. So this would be the 7th term in. Let's do our substitution. So substituting in -5 for a, -5 to the 1st, and plugging in 2y for b, 2y to the 6th. So calculating these things, -5 to the 1st power will stay -5, but 2y to the 6th power, 2 to the 6th power is 64, y to the 6th. So now I do need to multiply those things together. 7 times -5 times 64 is -2,240 y to the 6th. And that would be the 7th term in. Thank goodness we didn't have to do the complete expansion.